In our previous class, we have discussed about Q point, where the Q point will come in a characteristic graph. So we have discussed so many things about Q point and where comes the Q point and why it is important to make your transistor to work as amplifier. So we need an important thing that where your Q point should be at the center of the load line. It should be at the center of the load line. This is your DC load line. So this is a straight line drawn on the output characteristics of your transistor. Now I have drawn like this is a output characteristics of your transistor in C configuration. So we have drawn a diagram where we will be seeing a silicon transistor of some beta value. What is beta? So we have studied this in our previous year. What is beta? Beta is current gain of your transistor. In which configuration? C configuration. Isn't it? Yes. So we have beta. So beta is what? It is current gain of your transistor in C configuration. Isn't it? Final one. Yes. So here what we can see is, so we have defined beta, and different transistors will have different beta values, and current gain. So current gain varies. What is current gain? It is equal to your output current divided by input current. Isn't it? So I can say what is beta over here. It is output current is what? IC, and what is input current? It is IP, isn't it? So it is beta is equal to IC divided by IB. This is for common emitter configuration, isn't it? So now beta value will give us how much times will be your output than your input, isn't it? So it is output current is what? IC, input current is what? IP. So beta, if I say beta is 200, so your output current will be of 200 times than the input current, isn't it? Right? Yes. So likewise I can write what is IC here. IC is equal to, by this value we know that beta is equal to IC divided by IB. So how I can write IC? IC is equal to beta into IB, isn't it? So likewise we will have two of the equations wherein I can find out IC, isn't it? Yes. So when I know beta, IB or input current if I know, so I can directly calculate IC. So what will be the value of your IC for your Q point, isn't it? Yes. So from this equation, if I make some value of VBB, so that will make some current IB. So if I take let your IB be some 25 microamperes. If I say IB is equal to 25 microamperes, so what will be your IC value then? So it will be, IC will be 200 into 25 micro. Micro in the sense, what is that? It is 10 power minus 6, isn't it? 10 power minus 6. If I multiply that, so what will be the thing? What it will be? It will be 5 milliamperes. If you multiply these things, so you will get the sum equal to what? Or total equal to what? It is 5 milliamperes. So your IC will be somewhere here. This is 5 milliamperes. Okay, so if I take some DC load line is somewhere here. If I say, so IC value, this is your IC value wherein your Q point comes. Okay, for this circuit or for these values, for these resistance and your bias voltages, and for these current limiting resistors and the transistor of beta value 200. Okay, for this circuit, so I can design the IC value to be 5 milliamperes. Likewise, I can calculate the VCE. VCE I can calculate with the formula. So it is. So last class we have discussed about this, isn't it? So I can calculate the VCE value by the formula. Was that it is VC divided by RC, isn't it? So likewise I can calculate, and that will come out to be what? Some 5 volts it will come out to be. Here I can say VCE. So likewise, if I go for the intersection point, so this will be your Q point. Fine. So if I take some value for your IB to be some different value. So different value, if I go for something like some 40 microamperes if I take, so this will change the total calculation. So this will be 40 microamperes. If it is so and so, then this will be something different. This will come out to be 8 milliamperes. So then your Q point shifts somewhere to different region. Okay. So likewise, I can have here your IC will come. Okay. So likewise, different values of Q I can take in the DC load line. So this is intersection. So Q point is what? It is an intersection of your DC load line to the output characteristics. For this, what is this? This is for IB is equal to 25 microamperes for the circuit, isn't it? So likewise, if I consider, so this is a DC load line and this is your characteristic curve wherein it is meeting or it is going for an intersection point. So this point I can say it as what? Operating point or Q point. So this is very important. So for your transistor to work as amplifier, your Q point should be at the center of the load line. So if you bias your transistor with certain voltages of base to emitter and collector to emitter voltages with some resistors of this value, and you will make your IB to certain value, you will make your Q point to come over here. So likewise, we can design the Q point where it should come. Okay. So for normal switch working, so we need not want that Q point to come at the center of the load line. So it can be for your on switch, I can go for the saturation point, and saturation region I can go for, and for off switch I can go to cutoff region. So then it will be on and off. For amplifier, we want this to be at the center of the load line, and this is somewhat like no signal condition. Till now we haven't applied any of the input signal, or the signal which has to be amplified. Okay, so only bias thing has been done. So input voltages will be applied later. So before applying the input signals, so I want the transistor to work in a proper region, that is active region it should be, and at the center of the load line. Okay, when I apply a signal, so the IC value will vary, isn't it? So your Q point will shift, IC value will vary accordingly. So Q point will shift again. So that should not happen. So it should not go out of the region. Okay, so it should not go out of the active region. Active region comes somewhere here. This is your active region. Okay, or also we can say it as what? Saturation region too. Okay, yes. So this is how we'll be going for your Q point selection, and next we will see about the different types of biases what we can go for. For amplifier application, so we have to bias a transistor properly, isn't it? So sometimes we can for a transistor, like we need at least 2 of the bias voltages, isn't it? So with 2 of the bias voltages, we can bias the transistor to work as amplifier or whatever it may be. So for this particular application, we need to bias it properly. So we need 2 bias voltages. Sometimes we can do with single bias voltage too. So we can do the thing with single bias voltages too. So likewise we have different bias techniques wherein we can bias the transistor for your amplifier application. So we have different types of biases. Types of biasing we have fixed bias. This is also called as base bias. Second one we have as collector to base bias, feedback bias. And third one we have it is your emitter feedback bias. And fourth one is voltage divider bias. This bias is called as what? This voltage divider bias is called as universal bias. Out of four bias types, the voltage divider bias is very important and widely used kind of bias technique, that is universal. It is also called as universal bias. Universal bias is in all of the circuits we can use it without any problem, and it will be using only one bias voltage. So for different bias techniques we need different like we will be biasing the transistor in different ways. So this is fixed bias, that is also called as what? Base bias. This is collector to base bias, collector to base feedback bias. Feedback in the sense, so we will be feeding back the output to input. So likewise we have this collector to base feedback bias. So emitter feedback bias is the third type of bias, and finally comes the voltage divider bias. Voltage divider bias is very important, and for your syllabus you have only voltage divider bias to be studied, and this is called as what? Universal bias. Okay, sometimes they call it as what? Universal bias. So you will not get confused with what kind of bias it is. So it is universal bias is nothing but your voltage divider bias. So now we will see the voltage divider bias, how it is going to come, and universal like voltage divider bias uses only one bias voltage. Out of two bias voltage we can have the voltage divider thing, so that we can have only one voltage supply, so that will make the bias for both input and output terminals of your transistor. So we will see that this is voltage divider bias. Now we have come with the type of bias thing. This is your voltage divider bias, and here what I can see is your silicon transistor. I have taken a silicon transistor has been biased with 4 of the resistors. So this is a collector current limiting resistor. Fine. So this is your emitter resistors. We have collector, base and emitter. These are the terminals, isn't it? Yes. This is your emitter resistor, and we have two resistors R1 and R2. So these two resistors are very important. So voltage divider bias, the name comes from the truth that R1 and R2, these are the two important resistors which will divide the voltage. What is that? What voltage it is? It is VCC voltage, or the voltage which has been given as a single bias voltage. So this voltage will be divided across two resistors R1 and R2. Okay, so the applied voltage VCC will be divided across the resistors R1 and R2. Different voltages will be dropped across R1 and R2, and these voltages will bias the resistor. So here now we have this VCC. So VCC voltage will be coming to output terminal like in this direction, and here this voltage comes here, and some of the voltage will be dropped across R1 and some voltage will be dropped across R2. So the voltage across your R2 is very important because this voltage will bias your base to emitter terminal. So input terminal, base to emitter terminal will be biased by the voltage across your R2. This voltage is what V2. This is very important. So this is the voltage which is needed to bias your input terminal VBE. So that will make certain current IB. Isn't it? So this will make your current IB. So to make your output current IC. Okay. So when you have this IB, so you will have your IC. As you increase IB, IC also increases in this common emitter configuration. Fine? Is that okay? Yes. So applied voltage VCC will be coming like this in this direction, and here some of the voltage will be dropped, here the rest of the voltage will be dropped. Okay, so this rest of the voltage, that is called as P2, this is important. So this voltage will be dropped across this voltage will be biasing your base to emitter junction, or forward bias is the base to emitter junction. For your amplifier application, another important thing is that for your transistor to work as amplifier, your input terminal or base to emitter junction should be forward biased. Base to emitter junction must be forward biased. Base to emitter junction should be forward biased, and collector to base junction. This is a collector to base junction. Here it is. Okay, not the output junction. Collector to, not collector to emitter. It is collector to base junction. Collector to base junction should be reverse biased. Okay, so this is our condition. So for amplifier application, for a proper amplification, the condition is that base to emitter junction should be for C configuration. Okay, yes, base to emitter junction should be forward biased, and collector to base junction should be reverse biased, and C configuration is most widely used configuration. Okay, so because this has high voltage gain, high current gain, high power gain. All the things are best for this configuration of your transistor. So C configuration is used most. So because we have all current, voltage and power gain at this configuration. Okay, so this is your amplifiers. For this amplifier application, base to emitter junction should be forward biased, collector to base junction should be reverse biased. So we can see here, so it is an NPN transistor. So we can see that forward bias and reverse bias here. So this voltage will be coming here and voltage V2 will be dropped here, and the applied volt then dropped voltage across V2 will be biasing here or biasing the base to emitter junction. Fine, base to emitter junction it will be biasing. So see here, so it is a positive voltage which will be coming here, and we have a P terminal, so forward bias, isn't it? Isn't it or not? Okay, so here positive going to anode. Okay, so forward bias. Okay, so here collector to base junction, collector to base junction. If I see, so here you are getting the positive voltage. So here it is something different. Here positive voltage is coming, and here we have N terminal. So reverse bias, isn't it? Both the conditions becomes true. So then this will work as what? A proper amplifier. Okay, a best amplifier. So we need proper biasing for faithful amplification. What is faithful amplification? The amplification which will be not like the current level and the frequency also not. It is not at all going different. It is we are getting a proper stand, like what we can say stable. Okay, stable output current what we are getting. So then it is what is called faithful amplification. We can say it as. Okay, so likewise we have this voltages R1 and R2, and V2 is the voltage which will be biasing your input terminal, and the output. What happens is, so we have VCC and this is your RC, isn't it? So the voltage, likewise this VCC also coming to your output side. So VCC will come here and certain voltage will be dropped across RC. What is that? This voltage is called about VC. If I say that this voltage drop across your RC will be VC, and out of total voltage, what is that? VCC voltage, certain voltage will be dropped across your RC, that I can say it as what? VC, and remaining voltage will be dropped across your collector to emitter junction, isn't it? Collector to emitter junction, if I say, so this is your output bias voltage. So VCC I can say it as what? Some of the voltage will be dropped across RC and remaining voltage will be dropped across your collector to emitter junction, and I can say this as what? Output bias voltage. What is that? It is VCE. Fine. So this is your input bias voltage, and this bias voltage I can say it as VBE. What is this? This is VBE. This is your input terminal base to emitter bias voltage, and this is your connector to emitter bias voltage. This is your input bias voltage. This is your output bias voltage. VBE is nothing but your V2. Okay, V2 voltage will supply VBE, and this VCC which will be coming here, this will make your output bias voltage VCE. Likewise, so we can have only one power supply which will bias both input and output terminals of your transistor with two of the resistors, with two of the voltage divider resistors R1 and R2. So it is left to us to select proper value of resistors R1, R2, RC and RE for proper amplification or for proper bias voltages. Okay, so what amount of voltage you need across your input terminal or VBE? So I should select the resistors so and so. So they will make so and so voltage drop, and so voltage will be provided to the transistor input and output terminals. So likewise, we have this voltage divider bias, which will make use of only one bias voltage, and this is also called as universal bias. So this is very widely used bias technique, and it is used in all of the circuits. Okay, so this is how we will be going for, and in our next class we will be discussing about the equations on this voltages V2, VCE, and what all the things will be coming across this circuit, and we will continue the same thing, same topic in the next class. Thank you.